Okay, so the cMAKE build system for CFE. This kind of the genesis of this was a few years back when this whole notion of reusing applications, app store type concepts, mixing and matching pieces from different places was talked about. We've been talking about this approach to CFS for years, and making all these components highly reusable. And part of that, that implies certain things about those components that should be true. That source packages, if you're going to have an app store type concept, you want to ideally have like a package or something you can just download and drop into your build and have it work. You want to be able to version control it. You want to make sure that you can keep up to date with it. If there's bug fixes that other people have found, that you can get that. Because that's part of the advantage of sharing code, right? Is that other people find problems and you can get the fix. So you want to be able to not only integrate something easily into your build, but you want to be able to also keep up to date with it. And likewise, you might find a bug and you might want to submit that. So it flows both ways. You can reuse your code and get the benefits of other people's fixes, and as well, if you find some issues and create some fixes, you can send those back. So why change anything? I mean, the classic build as it had existed didn't quite work as nicely as one would hope for that type of model. Basically, the process involved with adding another application, it was a bit more involved than it should be, you could say. Could be more developer friendly. It had a number of hand-edited files and manual operations to change things. If you integrate a new app, there was several files that had to change along with it and several clone and own type operations. It also had a lot of task-specific data in version-controlled files, and we'll get into that a little bit more. But basically, it as far as a workflow point of view, we found some issues with it that just made it a little more difficult to work with than what we would have liked. So anyway, okay. So I think part of the root of the problem really with the classic design is the two-part nature of a lot of the Makefiles. So you had this, let me see if the pointer works. So this outer build tree is something that you would clone and own. So as you deploy your mission, you'd copy these Makefiles that then referenced Makefiles that were included with the source. But there wasn't one Makefile for an application. It wasn't one recipe. It was kind of this two halves of a recipe. And even as recently in the 6.6 development, basically these are more tightly coupled than they should be for this type of modular environment. We ran into a number of situations where a change over here on, for instance, CFE-ES broke this half. And if you're a mission and you have this half already in your build and you're trying to upgrade to this half, we don't want to break it. That's bad. But there's really no way around it, because it basically it meant there's a change over here, or sorry, a change over here that had to be propagated or mirrored on this side. So that's part of the major problem that we're avoiding. And there's other issues too, like with respect to mixing version-controlled objects with non-version-controlled objects, generated objects, and things like that we also hope to avoid. So how does cMAKE work differently? Basically, it's just a tool that generates the Makefiles. So at the end of the day, you're still using Make to build your project. It's still GNU Makefiles, or just standard Unix Makefiles. But what it does is it adds another layer of control and another opportunity to customize things and introduce an intelligent translation. So basically we have information coming from a lot of different places, and four major ones really. There's your mission specific, your table definitions, the selection of apps that you're using, your how you're laying out the system basically. The second input would be your board support. You know, which boards are you using? What cross compiler are you using? What tuning flags do you want to use for that cross compiler? The third piece is just general preferences. How many warnings do I want? What level of optimization do I want? Because many times as a developer, if you're debugging something, you may need to turn off optimization in order to get useful debugging output. So that type of thing is more transient in nature. It's whatever job you're trying to do or whatever problem you're trying to solve might affect what goes into here. And finally, it's the collection of applications that you're running. And each application should be modular with respect to you bring this application down, you drop it in, it's the same recipe to build that application. It's just all this other stuff on the outside might be different. So the idea here is let's specify each of these things in one place and try not to repeat it. So the Makefile system can, at the time that you prepare your project and initiate a build, we can put all these things together and generate a set of Makefiles that'll work for you and avoid the hand editing part. So some other advantages that you get from using this tool, it does a pretty good job of dependency management. So all the generated Makefiles have deep dependencies for header files that you've used. So if a header file includes another header file, which includes another header file, and you change that one that's way down at the bottom, it will reliably rebuild all the other stuff that goes along with that. And that's kept up to date. So if you change it and you add another header file, there's no separate make depend step or anything like that. It just, everything's automatically kept up to date and it works. The other thing we can do, because we have this scripting layer in the middle of the, between the Makefile recipes and the actual generated Makefiles, we can offer opportunities for missions to override files. So you no longer necessarily need to customize files in place. You can keep the original source of your app that you downloaded pristine. You offer an override file in your local area. That keeps you compatible with future releases. When you pull down the next release, it's not going to overwrite your change. You still have your override file separately that isn't going to be touched. So there's a number of other advantages you get. And there's other optimizations that can be done. For instance, I mentioned the developer preferences before. Those type of things can be specified just once when you set up the build. They don't necessarily need to go into a version controlled file, so you can quickly change your target. If you happen to be developing locally on a workstation for debugging, you can quickly change to a emulation target, or you can build for the real hardware without having to edit files. Because it's very easy to, if that was in a version controlled file, it's very easy for developers to kind of thrash around on that. One person's working on the workstation, one person's working on a piece of hardware, and you don't want those two to fight. So it's really specific to that developer and how you're setting up that particular build. So to get into a little detail about these ingredients that I touched on earlier, the mission specific is, of course, your app selection, table definitions. To get started with this, the cMAKE distribution, or the CFE distribution comes with a sample definitions directory that you can use as a starting point. So instead of having to figure all this stuff out from the ground up, you can pretty much just clone this sample defs directory into your top level, start editing it, and because you've cloned it, because you're editing a copy, if a new release of CFE comes out, you haven't changed the original, you can easily diff between them and apply that patch to your clone. So it makes migration to the next version easier. It's the whole reason for keeping the original copy pristine. So to give a little more detail about what's in that directory, probably one of the, it's basically all the things that you would typically edit for your particular mission deployment. You've got the startup scripts for each of the CPUs. You've got the OS config files for your various platforms that you're using, as well as the platform config file. And you've got your mission config file, of course, and probably one of the bigger ones is the targets file. This is where you spell out what your targets are, what the cross compiler is to compile for that target, and what apps you're going to run on that target. And here's just a snippet of what would be in that. You specify the name of your CPU, the toolchain file that you're going to use to build it, the configuration, the platform config, and the collection of apps that you want to run on that CPU, as well as this is actually just a free-form list of files to copy in. So when the build completes and you run the installation step, it's just going to search for a file by this name in your definition directory and copy it out to that install directory. So it's very useful for things like the startup script, where you want to customize that per board. So the board support, cross-compiler tuning flags, these come from the BSP. And it starts with the toolchain file. The toolchain file is actually something that comes from the cMAKE project. It's basically just a bare bones set of instructions as to how to run your cross-compiler, where your cross-compiler is, if there's a minimal set of -M, -F, CPU architecture selection options that you need to supply, it goes in the toolchain file. So it's how to build just the minimum you need to build a C file for any given CPU. Now the PSP and OSAL can in turn extend that. So each of the components can have an options file within it that can append additional flags. And some examples are for the POSIX OSAL, we typically need to specify x open source equals 600 or something to enable some of the real-time POSIX API calls that are not necessarily available by default. Developer preferences. These don't actually get stored in a file at all because they're intended to be tuned for the task at hand. So when you start a build, you'd specify these just in the local environment. But obviously you don't want to have to specify it every time you run make. So basically you only have to specify it the first time, and once you specify it and you have your make files generated, it is then cached. So it's kind of baked into the make files. You don't need to worry about it thereafter. There's no set vars or anything that you need to source in your environment. You just change the directory and you run make, and it just works. Another example would be this simulation variable that can come from the environment. And this is a nice, I use this all the time to compile for the native platform. So basically what it does is override the setting that you specify. If I go back a couple slides, in the system configuration, you specified a toolchain file to use. Basically, you're saying at setup time, forget about that toolchain. I don't want to use it. Just use the native compiler. And what it will do is it'll just compile all the code, same configuration, same structure of apps, same CPU arrangement, everything of that nature. It just builds everything with the local compiler. And then you can run it on your workstation. So without editing any files, you have a workstation build. So it's very useful for debugging. Another useful variable here is the cMAKE build type. This is also a feature of cMAKE where you can control the optimization level, among other things. But you can specify to do a debug build, which generally means no optimization, or a release build, which turns on most optimizations. So you have that control at setup time as well. And finally, there's a kind of a generic means to add additional options in through this OSAL user C flags, which any additional flags that you want to use will get baked into the Makefiles. So I often use it for turning on all WAir when I want to make sure I have scrubbed all the warnings. Finally, probably the most obvious part is, of course, all the application recipes. So once you have all these kind of metadata, each of the applications should have a recipe to build that particular application. It just says what the C files are with that application, what its dependencies are, and any other special sauce that needs to go into that particular application for a build. So to get into a little more depth on the directory structure and how these pieces get put together, your top level layout, probably a lot of people who've used CFS are now familiar with this, but basically each of the CFE, OSAL, PSP subtrees, these components that come from the shared Git server or wherever you happen to be getting yours from would get put together into a top-level directory along with your mission configuration into your build. And all the applications should typically go under apps, although the cMAKE does allow additional directories here. You can have a libs directory, and you can even specify your own. If you have you can even have apps outside of your work tree that the cMAKE build can still find them if you provide a pointer to it. So basically, all of your components get assembled here.
Where do you supply that pointer? Without going back too detailed, if it's too
detailed. It's another one of the environment variables. I would have to double check the source to tell you exactly what it is, but it's another environment variable that you can specify essentially a search path for all of your application source code. So when you set up when you run the preparation phase, it's actually a search that goes. So if you've specified a bunch of apps in your targets.cMake file, it will search through that search path to try to find a matching directory for that application. It says, oh, there's a name match, that must be the source for that application. So you can extend that search path if you so choose. To clarify where those BSP and OSAL option sources come from, there's couple magic files. They're called build options.cMake, and you'll find them under the PSP and under the OSAL. And these are just the snippets that extend the C flags for that particular platform or operating system. And again, a sample of an application recipe. Basically, it's just a cMake list.txt at the top level of that application's distribution. A typical structure for an application, and this is going to become more and more important in the future to make sure that we've delineated between what's a public include file that other applications are supposed to reference and will hopefully have some version stability over time versus what's an internal use only header file. And those should be well defined as to which is which. And generally the private source files should just be under the source directory. We don't really care about what's in there. There's no rules there really. You just have to list out what your source files are. But the preference would be to put all of your public include files that other entities are intended to reference in a separate directory. And a typical cMake recipe would just, first of all, indicate all the directories that this particular module needs to reference. So all the other places that it might find header files. A number of directories are kind of in there by default. That includes the CFE and OSAL include directories itself, but you can specify additional ones per application, depending on what your dependencies are. And this is just a kind of a quick and dirty way to just say all the source files in FSW source go into a single executable or a single shared object called CFS lib. And this question has come up a number of times: is how do you specify additional third-party libraries that apps depend on? And even though CFS lib doesn't technically depend on the math library, this is how you would do it. Basically, it's a standard cMAKE call called target link libraries, and you just specify the object name, and you list out the libraries that it depends on. That's basically all there is to it. This works on a shared object system. RTEMS tends to be a little more finicky about it. It still works, but you might have to load it manually. So there's just some additional gotchas in systems like RTEMS that don't have like a true true virtual memory type environment. So I talked about generating the Makefiles, and when you run this preparation step, it generates this build directory, and you'll end up with this type of structure on your system. And one important point that's not really spelled out here, you can have multiple build directories in parallel. So from one source tree, you can have 2, 3, 4, however many you want, build directories with different configurations, because they're all self-contained pretty much. You can delete them, recreate them, whatever you need. They would never be checked into version control because these are all generated files. So a theoretical mission here with 3 CPUs, let's say CPU 1 is a main processor, PowerPC Linux. CPU 2 and 3 would be RTEMS as helpers for data collection. So these would be fairly small processors. Typical directory structure that you would end up with after preparing your build, you'd end up with two major subdirectories at the top level. Each architecture in use gets a subdirectory. So basically, it goes by toolchain file, and everything sharing that toolchain file gets built under this directory. So everything built with the i686 RTEMS 4.11 ends up getting built in here. Everything built with the PowerPC toolchain gets put in here. And once everything's all built and you run the make install step, that's where it copies it out into a directory structure that you can actually install to your target. And we don't get into how to actually install it to a target because that's too varied, but it'll just copy the files out wherever you ask it to copy the files out. So an important note is about the scoping of include files, and I've talked about this a number of times, is not all include files are applicable everywhere. It's very important to only reference those definitions, those types that are scoped to the same thing that you're actually building for. So the cMAKE build attempts to enforce this by actually putting the more narrow scoped include files in a subdirectory. So when you say you have a CFE platform config file, it actually buries that down inside the build directory for the CFE core that it applies to. So you'll actually have several of them depending on how many CPUs you have in use. Each build of the CFE core gets a dedicated CFE platform config.h file that lives down with that code. And on the other side of the coin, the things at the mission scope that are intended to apply across the mission as a whole get put in a very top level include directory. So you'll see a number of include directories in your output tree, and the reason for that is the scoping. It applies basically to the directory immediately above it. So this include directory applies to all things i686 RTEMS, whereas this include directory applies just to the CFE core. And that's how it controls the scope. So this, of course, does have some impact. In historical usage, there wasn't a strict rule about what could include what. So you did end up with a lot of apps including platform-specific configuration. Ideally, that's not ideal, and there are risks there because if you have an app and you build it one way and you change something about the CFE platform, there's always that chance that you could introduce some binary incompatibility or something changes with respect to the platform config that causes memory alignment to be off. because platform config can change sizes of structures. So, and I've personally run into this when debugging and some real head scratcher problems. And because one app was built with a definition one way and another piece of code was built with a definition a different way, and they didn't necessarily get the same one. In fact, just recently with the CCSVS version 2, I had one file that was compiled with the 32-bit message ID and one with the 16-bit message ID, and it just really weird stuff happened. So anyway, hopefully we can migrate away from that. But there is a workaround because this was a practice that had been done before, and we need to maintain compatibility. If you set up your missions such that there's a one-to-one relationship between tool chains and CPUs, it very closely mimics the old behavior, where everything is built per CPU. And in that case, the risk of mixing and matching platform configurations is low, so we let you do it. There's actually a special piece of code in there that says if that condition is met, where you have a one-to-one relationship, go ahead and add the include path, even though it violates the scoping rule, so that this still works. So it maintains the compatibility until we can clean all that stuff up. So that's kind of the high level of how it works and what you get when you run the cMAKE build. It is a bit of a transition, but hopefully it will make things a little more modular and a little more stable in the long run. Yes.
This is in 6.6.
This is all in 6.6. It started in 6.5, and it's been refined further in 6.6. So, yes.
Well, to use the electronic data sheet feature 6, you have to
Yes.
use, that's a...
Yes, the electronic data sheet feature, when released, ties in directly with the cMAKE, and part of that, the scripting features of cMAKE are pretty critical to that, because we can run the tool and everything at the right time in the build with the smarts necessary to do that. And the cMAKE runs through and collects, for instance, if your apps have electronic data sheets in them, the cMAKE scripting language offers us the ability to actually find them, identify all the EDS files that you have supplied with the app, so it makes the whole process pretty automatic, whereas you'd be hand editing a lot of files without it. So, yes.
I've been using the cMAKE tool to build the CFS, and in the toolchain file you have the app list. The app list has the list of all the apps that you should build.
Right.
And it seems they are built in the order that they appear in the list. And so for some libs, you should put them before the apps that use it. And also apps like schedule should be put in the end because it uses .h files from other projects or other apps.
Well, this,
Yes, something like that.
the order of these as listed here really shouldn't matter. It may build them in the same order.
No, yes, I had that problem. When I put my scheduler before the apps, it does not find the .h files that comes from the other apps. And I would like to know what to do when I have some kind of cyclical dependency in the apps.
Well, each application, let me see if I can find sorry, I have to come.
Can you read the question?
So the concern was regarding the order of applications as listed here in the app list. It sounds like the issue you observed was a failure to build based on the ordering of these apps.
Joe, actually, I know.
In the configuration file in the app that was missing, I
So,
covered the destination app with the name of the project and not the
I think he's he may be, this particular, the one with scheduler out of the box references the sample app message
I
ID
think-
IH. And so cMAKE barfs because cMake's trying to trace down all the dependencies and says, I can't find sample app.h.
Yeah,
So, not
that
necessarily,
I would concur. Yeah, there are some apps that don't follow all the recommended practices for this. I think the main thing to do, let me see if I can find the slide. When specifying the dependencies, I think the most important thing is to use the, I know I had it in one of these slides, now I can't find it. Basically for all the components, that, oh here it is. For all the components that you have in your targets.cMake file. As I said, cMake follows a search path. So if you've listed half a dozen apps in your targets.cMake file, early on in the process, before it even tries to build anything at all, it's going to search your hard drive to find a directory with a matching name for that app. And that's how it identifies where all the apps are. And when it finds it, it stores the full path name to it in a variable of this form, where it has the name of the app followed by underbar, mission, underbar, dir. So if you have in your recipe, if you depend on, say, CFS lib, if you specify it like this, where you use that directory and not any assumed path, you should be safe. You know, that it should be portable to other environments transparently. And this should remove the dependency on anything being built before anything else. If you're,
I can show you my
yeah, if you're having specific problems, feel free to send me an email, because I can possibly offer some more specific guidance on that. But it really shouldn't depend, the app list order in your targets.cMake file shouldn't matter.
We have a few questions from online.
Yep.
Turn the mic. So these questions are from ZZ Dixon online. First, is it possible to run CFE on Raspbian instead of Ubuntu? He's tried it using QEMU, but it didn't work at all on his PC.
What was the end of that?
Is it possible to run CFE on Raspbian instead of Ubuntu?
Yes. Yes. The short answer is yes. The Raspbian is basically just a Debian OS for ARM. You have a few choices when you operate in that mode. If you have the full Raspbian installation with a compiler directly on the box, you don't need to worry about cross-compiling. So you can actually, if you install the native packages for cMake, for your compiler toolchain and everything of that nature, you're essentially back to a native build again, just on the Raspberry Pi. So you can just use all the native tools. The other option is to put on the cross-compiler for Raspbian on your development host. That's the mode of operation I typically work in. I don't like to compile on the machine itself because it's very slow. So you can oftentimes get a lot more efficient workflow by building on your host and then just rsyncing the targets over.
Tell him that he needs to make sure that he has POSIX message queues turned on in his kernel. I've seen a lot of ARM
Yeah,
defaults.
good point. You need to have the POSIX message queues turned on in your kernel. That is a toolchain option. That if you don't have that, then OSAL will have problems.
Yeah, I believe I've seen the same issue myself over here.
Yep.
And I believe that also answers his second question online. And his third question, is there an updated CFE version that includes 0MQ Python library and documentation showing a working example?
I believe there is, but I cannot point you to it. I have heard a lot of talk of such things. I know people have done that type of thing. But
I'm working on that.
Yep.
I don't have anything online yet.
So
That's it for the
Alan
online
Cudmore has
questions.
been working on something, but he doesn't have it released or online yet. There's another question back here? Yeah.
Yeah, in our setup,
In our cMAKE setup, in addition to the tables, having mission-specific tables in your mission def directory, we also have files, default files that we want to fly with, image files, for example. Is there plans to add this type of generic capability?
Yeah, so you can, there's a few ways to approach that. So this, if your files are just like binary blobs that you just want to copy in, you could just put any arbitrary files here and list them under the file list, and that's just a straight copy. The other thing you can do, and I don't have it, it's not in this chart, but I do have an example of it on my laptop, which works. During the install phase, you could tell cMAKE to run a script. And that's documented. If you go to the cMAKE documentation, which all the commands and everything are pretty well documented, there is in the install function, there's a script mode that you can say, at install time, run this script. So you could kind of use that to make any arbitrary, if you need to generate the file or do any sort of special processing on it during your final copy stage, you can do it that way. And for instance, if we have one project that utilizes an embedded web server, so it needs a little config file generated to have it point to the right root directory in the install. So for that, it uses basically what's a template for that file, but then uses the script mode so that when you actually install it, it generates the right thing.
Okay, thank you.
Yep.
Is there an example app that has like EDS in it? That's, it shows how the, with 6.6, I guess is the implied interface.
Yeah, in 6.6, we have the EDS files for all of the core applications, so ES, SB, EVS. They all have associated EDS files with them. I also have CI and TO lab versions with the EDS file that goes with them. EDS files for some of the other apps are in progress. And we did write some in the course of a previous project for a number of the apps. I think LC, stored command, scheduler. So we have those, but they're not fully complete yet, or at least not in the repository yet. And we can work on that. I don't know. Yep.
All right, well, thank you, John.
All right. Thanks.